And I think we're probably ready to start. Paul, is there anything else that I should have covered and haven't?
No, I think that's all good to go, Rob. Thank you.
Okay. So I'm going to be showing a number of I've got basically a slide presentation here. Please let me know if it doesn't seem to be showing correctly, but hopefully that will be fine. So Paul, that's all right? Paul, can you see that okay?
Not yet, Rob.
Oh. You can't see this? How about some of the students? Can somebody tell me if you can see the slide?
I've got it now, Rob. It's fine. Yep.
Oh, good.
Yep.
Okay. So I'm going to review the physics lectures that you have done so far, which is obviously a fair bit of material. So I will be moving fairly quickly through it. So we'll start with the first lecture, which covered ultrasound properties. And we talked first about wave properties. So the fact that the ultrasound is in the form of a wave. It consists of pressure variations. So the pressure in the tissues increases and decreases in an oscillating way. We therefore have a whole lot of variables. We have the pressure itself. We have the frequency of the oscillation, the period, the amplitude, wavelength, and the propagation speed. And this is one of the graphs that illustrates that. So just the general concept and terminology around the wave. Has anyone got any questions about that? Okay, so the next very important topic that I covered is that of attenuation. As ultrasound travels through tissue, it heats the tissue up. So the tissue warms up by a small amount, by perhaps a fraction of a degree or a degree, something of that order. And that heat energy remains in the tissues. This means that energy is being taken away from the ultrasound wave and converted into heat by the tissues. So the ultrasound wave gets progressively weaker and weaker as it travels through the tissues, and this is what we mean by the term attenuation. The main cause of attenuation is therefore the absorption of energy by the tissue, and that energy causes the tissue to become hot or warmer. Now, to calculate the attenuation, it turns out there is quite a simple formula if we use decibels as the units of attenuation. And I'll talk a little more about this shortly. So to calculate the attenuation, we simply take the attenuation coefficient of the specific tissue that we're talking about. Different tissues will have different coefficients. So if I was looking at a large uniform organ like the liver, I would be using the appropriate attenuation coefficient for liver tissue, which might be around 0.5. That attenuation coefficient is then just multiplied by the distance traveled in the tissue by the ultrasound and the frequency of the ultrasound itself. So it's a simple product of three things, and that tells us how many decibels of attenuation there are. The attenuation is very substantial. So in typical situations, when we're looking deeper in, the attenuation may range from perhaps a factor of 1,000, but perhaps as much as a factor of 1,000,000, which means that echoes from the maximum depth in the image may be 1,000,000 times weaker than they would have been if there was no such thing as attenuation. So the attenuation has an enormous effect. It dramatically reduces the echoes, particularly as they're coming from deeper into the tissues. In fact, the attenuation limits how deep we can scan. And it turns out that the penetration depth, the term that we use, depends on frequency. Now, what we mean by penetration depth is that's the maximum depth to which we can scan. Echoes from deeper tissues won't be seen or won't be seen comprehensively, and so we can only scan to the limits of the penetration depth. So the penetration depth depends on frequency, and their relationship is very simple. The product of frequency and penetration depth, so the two of them multiplied together, is a constant. So if I increase the frequency, the penetration depth must decrease. If I decrease the frequency, the penetration depth would increase. And so what we see is that we have to use relatively low frequencies when we're scanning deep, and we can use higher frequencies when we're scanning more superficially. So in the end, we have a rule of thumb which helps us to choose an appropriate frequency for any given application. And that is that we will use the highest frequency that we can that gives enough penetration for the job in hand. So for cardiac imaging, you need to penetrate quite a large number of centimeters, and therefore the frequencies are relatively low. For scanning the carotid artery, you are only penetrating a couple of centimeters, the frequencies are much higher. So the frequency will vary dramatically depending on the area of use. Another story entirely is invasive probes. These are used to get very close to the area that you're interested in. Transesophageal probes, for example, get very close up, normally to the aortic outflow. And this short distance means that much higher frequencies can be used than if you're scanning transcutaneously. So invasive probes get close to the target tissues. They can therefore use high frequencies, and therefore they provide excellent resolution. Later on, I'll talk about frame rate, which is the number of images per second, and invasive probes also will give excellent frame rate for the same reason, because they're close to the area they're scanning. So are there any questions at all about attenuation and its implications? Okay, well, we'll go on to the various other interactions between ultrasound and tissue. And one of the most important, because it's a source of the ultrasound echoes that we use to make the image, is reflection of ultrasound, which occurs whenever ultrasound hits the interface between two tissues. Say, for example, the boundary between the liver and the kidney, or between the liver and one of the blood vessel walls. So whenever ultrasound strikes a tissue interface between two different tissues that have slightly different acoustic properties, some of the energy will be reflected and the remaining energy will travel through into the deeper tissues. How much of the energy is reflected depends on how different the two tissues are. If you have two very similar tissues, there'll be very little reflected. If they're very different tissues, then a lot more energy will be reflected. In an extreme case, if you have ultrasound traveling through soft tissue and then striking bone or air, virtually 100% of the energy is reflected because the acoustic properties of tissue and bone and air are so very, very different. In fact, we can calculate the fraction of energy that is reflected using this equation, which tells us that we use a property of the tissues called acoustic impedance. The acoustic impedance is simply propagation speed of ultrasound multiplied by the density, and it will vary from one tissue to another. So when I want to calculate the reflection amount of energy reflected between two specific tissues, I'll be using their specific acoustic impedance values, and I calculate it by taking the difference between the acoustic impedance values divided by the sum of the acoustic impedance values, and all of that is squared. This will give us a number between 0 and 1. 0 means there's no reflection, 1 means all of the energy is reflected. The other important thing to say about reflection is that it has a specific geometry. and it's exactly the same as it is with light. If I look at this diagram, what I've done is drawn a dotted line, a reference line that is perpendicular, in other words, at right angles to the tissue, and I've drawn it at the point where the reflection is occurring. I then measure the angle between the incident beam, in other words, the beam coming from the probe, and that's theta with a subscript I. And then I have the reflected angle, theta r, which is the angle between the reference line and the reflected beam. And the rule with reflection is very, very simple. Those two angles are equal. Now, if you think for a moment about the implications of this, what we see is that the echo produced by the reflection in this diagram is going to go off somewhere else and not return to the probe. So it won't be detected. It's lost. It's not going to be part of the image. In fact, the only time that echoes will be detected, echoes from surfaces like this will be detected, is when the tissue interface is at right angles to the beam. And we call this perpendicular incidence. So perpendicular incidence, the echo will return to the probe and we'll see it in the image. With other angles, not perpendicular, the echo goes off somewhere else and is lost to us. Any questions? So there are two different things that contribute to the echoes that make up the image. The first is reflection, the second is scattering. This is an image of liver tissue, normal liver tissue, and you can see that it has the typical grainy sort of texture and appearance that we know is typical of ultrasound images. That is something that we call speckle, and it's produced by scattering. So ultrasound, as it's passing through soft tissue like this liver, scatters from any small tissue structures that it encounters. So these may be small blood vessels, lymphatic vessels, small functional structures within the liver, etc. Anything that is small causes scattering. What we mean by scattering is that instead of a single reflected beam, we get ultrasound sprayed in all directions, which means a little bit of it will go back to the probe and will be detected. So every single scatterer in this liver will produce an echo which the machine detects. At any one time, there will be a whole lot of scatterers producing scattered echoes, and those scattered echoes are going to combine together to produce the echo signal that the machine detects and displays. So it's looking at the mixture of many echo signals at each moment. The echoes actually arrive randomly at different times, and so the echo amplitude is going to be affected by how those echoes happen to add up. Sometimes echoes add up to reinforce one another, sometimes they add up in a way that cancel one another out, and so we get the variation in amplitude that we call speckle. So that's how speckle happens. So speckle is actually an interference pattern, a statistical phenomenon, not a direct reflection of the fine structure of that liver tissue. And that's an important thing to understand. Now, speckle is often regarded as a problem because it makes it more difficult for the user to see subtle variations in echo strength in an organ like this, like the liver. If somebody was looking in this liver for metastases, for cancer secondaries, they would be looking for variations in echo strength in the soft tissue. It's harder to see those variations when you've got this speckle pattern. It distracts your eye. And so the manufacturers have introduced some techniques to try and smooth out the speckle and make it less obvious. So somebody's got their sound on. If they wouldn't mind turning it off, we're just getting some distracting extraneous sounds. Thank you. So reflection and scattering are the two mechanisms then that produce the echoes that create the image. Any questions about that? So one last form of interaction between tissue and ultrasound is refraction. And this also happens with light. This occurs when the ultrasound passes through an interface between two tissues. But in this case, it's two tissues that have different propagation speeds. When I was talking about reflection 2 slides ago, I was talking about tissues with different acoustic impedances. Now we're talking about different propagation speeds. So whenever there is a difference in propagation speeds between two tissues, the beam will change direction as it passes from the first tissue into the second. Here's a diagram illustrating the idea. The beam comes down, strikes the interface between the two tissues, and it changes direction. Once again, the geometry is defined by drawing a perpendicular reference line and measuring angles relative to it. So again, we have the incidence angle, but now we have the transmission angle, which is the angle between the beam that's transmitted through the interface into the deeper tissues. And that angle is a measure of whether the beam has been deflected or is traveling in a straight line. Now, if the beam did not change direction and was indeed just a straight line, then theta I and theta t would be equal. Whenever they're different, it automatically means that the beam has been bent. It's changed direction and headed off in a slightly different direction. How do we determine how much of this refraction occurs? Well, it is determined by this equation down the bottom left, which is called Snell's law. And it says that the sine of the incident angle divided by the propagation speed in that first tissue is equal to the sine in the second tissue, the sine of the transmission angle divided by the propagation speed in the second tissue. One of the things we can see right away is that if C1 and C2 are the same, the angles must be the same. In other words, there's no refraction. If C1 and C2, the propagation speeds, are different, the angles must be different as well. And therefore, this refraction effect will occur whenever the propagation speeds are different. Once again, there is a special case. And once again, it's our friend perpendicular incidence. So when the beam hits a tissue interface at 90 degrees, it won't be deflected to the left or to the right. It will go straight through regardless of the propagation speeds. Now, refraction is generally pretty unimportant. It can cause minor distortion of the image, but I emphasize minor. But there is one particular artifact, which I think we'll be talking about next term, which is known as the ghost artifact or the refraction artifact, and that can be quite significant. So it just occasionally jumps out at you and produces a potentially very misleading artifact. So that brings us to the end of the first lecture, and I'd like to ask again if anyone has any questions before I move on. Okay, so the second lecture talked about how the machine makes the image. And the first thing is what we refer to as the pulse echo principle. The machine transmits a pulse of ultrasound and it receives echoes back from the tissues. And we've seen that those echoes are produced by a combination of reflection and scattering. For every echo, the machine can calculate the depth that it has come from by just looking at the time that particular echo arrives. So the machine takes the echo arrival time t, multiplies that by the propagation speed, divides by 2, and that must be the depth that echo has come from. So you can see as long as the machine knows the propagation speed, it can calculate the depth that every single echo comes from, and so it knows where and how to display it. The machine assumes that every tissue has the same propagation speed, that is 1540 meters per second. And that's one of the essential assumptions built into the making of the image. The next thing is that the transmitted pulse travels along a well-defined pathway that we call a beam. So the beam defines whereabouts in the tissues the transmitted ultrasound pulse travels. And so it travels only through the tissue within that beam, not outside of the beam. That means that we know that echoes must be coming from within the beam. Echoes can't be coming from other places. And so the machine knows the depth the echoes have come from, and it knows that they've come from within the beam. The only thing is the machine does not know just exactly where in the beam the echoes have come from. As this diagram shows, one reflector, one scatterer might be on the left of the beam, and another one might be on the right-hand side of the beam, but the machine has no way to know this. All it knows is that it's got echoes coming from within the beam at specific depths. And so it displays all of the echoes along a single line, which represents the central axis, the middle of the beam. And that's another essential assumption the machine has to make, because it can't determine whether things are coming from the left or the right or the middle of the beam. It displays everything as if it was in the middle of the beam. And that quite significantly degrades the image. So what I've described so far will give us the echoes for one particular position of the beam. The machine has to move the beam around, and we call this scanning. So the beam is moved to a series of different positions, one by one, and in each case, the machine transmits and receives echoes and then moves to the next position, transmits, receives echoes again, etc. Someone's having a nice drink, but with their microphone on. If you could mute the sound, that'd be great. So the machine moves the beam to a series of different positions, transmitting and receiving echoes in each one of those positions. And it does this methodically to scan the entire region and produce a complete two-dimensional image. A very important rule applies to this, and that is that the machine, after it's transmitted, has to wait until all the echoes that it can detect have come back before it moves the beam to the next position and transmits and receives again. If it doesn't obey this rule, we get an artifact called range ambiguity, which causes tissue structures to be displayed at the wrong depth. So this is an essential rule, and it limits how quickly the machine can make each image. If you're scanning to quite great depths, to large depths, then the time that the machine has to wait for the echoes to come back is relatively long, and so it takes quite a long time to make each image, and there can only be a small number of images each second. When you're scanning very superficially, the ultrasound's only traveling a short distance. The machine only has to wait a short time before it can move the beam, and so it can make many more images per second. So the imaging frame rate, the number of images per second, is limited by the depth. Linear and curved probes move the beam, scan the beam by stepping it along the face of the probe. So the beam might start off on the left-hand end of the probe and progress by small steps, perhaps less than a millimeter in size each step, until it eventually reaches the right-hand end of the probe, and then you'll have a complete image. There may be something like 200 different beam positions in a typical linear or curved probe image. The phased array or sector probe used in echocardiography is different. There, the beginning of the beam, the origin of the beam, stays fixed in the center of the probe, and the beam is pointed in a series of different directions. And we refer to this as steering the beam. And so the machine steers the beam in about 100 different directions in order to acquire a complete sector image. So that's how the machine scans the beam and acquires a total image. I just want to talk briefly about the resolution of ultrasound images. Resolution refers to the clarity of the image, but when you want to get technical about it, you talk about whether two small objects close together can be seen as being separate, in which case you say they have been resolved, or whether they blur together and look like a single object, in which case they have not been resolved. Axial resolution talks about the resolution in depth. In other words, how close together two things can be in depth and still be seen as two separate things. For the vascular people, a very good test of this is whether you can see the intimal layer of an arterial wall, because that's very close to the remainder of the wall of the artery. You're looking at very closely separated objects. And the axial resolution, it turns out, is related to the length of the transmit pulse, what we call the transmit pulse duration. And in fact, the axial resolution can be calculated by using the same equation I showed you 2 slides ago. Take the transmit pulse duration, multiply by propagation speed, divide by 2. The propagation speed is typically going to be a microsecond or less, and you'll find that that means that the axial resolution is a millimeter or less. That's very good, and we're going to see shortly that that's a lot better than the other aspects of ultrasound resolution. So the lesson from this is that the resolution of ultrasound in depth is much better than in any other direction. And this is yet another reason why you often need to try to scan tissue interfaces at 90 degrees at perpendicular incidence to get the greatest clarity. Of course, the machine needs to make the transmit pulse as short as possible to maximize this resolution, and it is designed to do just that. The next aspect of resolution is termed lateral resolution, and that's, if you like, sideways across the image. And in this case, the rule is actually very simple. For two objects to be seen as separate, they must be further apart than the width of the ultrasound beam. So the ultrasound beam width actually determines the lateral resolution. The beam width is usually several millimeters, and so the lateral resolution is going to be several millimeters. I mentioned a minute ago, the axial resolution is usually less than a millimeter or around a millimeter. So you can see there's a substantial difference between the two. Lateral resolution is poorer. So the ultrasound beam obviously needs to be made as narrow as possible, and I'll be talking about the focusing of the beam shortly. But one thing that is very easily said is that if you increase the ultrasound frequency, it will automatically follow that both of these resolutions, axial and lateral, will improve. So as you increase the frequency, the resolution automatically improves. Any questions? This is actually an image of an ultrasound test target, or phantom, and it contains soft tissue type material, which we're not interested in at this point, but it has a whole series of targets. And these targets are very thin nylon lines, less than a millimeter in diameter, and they go perpendicular to the scan plane. So the machine should be scanning them in cross section, and they should ideally look like little white dots in the image. Instead, you can see that each of those point targets is shown as a line in the image. The lines have a little bit of thickness to them, and that's the effect of the transmit pulse duration. And you'll notice that that thickening in depth is uniform. It's the same everywhere in the image because the length of the transmit pulse doesn't change with depth. It's the same always. So the thickening in depth relates to the axial resolution and the transmit pulse duration. The smearing out in width is variable and is substantially larger. You'll notice it's better closer up to the probe where the beam is relatively narrow, and it stays good until about the middle of the image, which is where the focus has been set. And then as we go deeper beyond focus, you'll notice that the blurring laterally gradually gets worse, indicating the beam width is increasing. You'll also notice, if you look at the points where a measurement has been made, where the little X markers are, that the lines out there are bigger. So right near the edges of the ultrasound image, the resolution is actually worse, the lateral resolution. And that's not uncommon. So a lesson from that is, when you want to see structures clearly and perhaps make measurements, make sure they're not right out in the fringes of your image. Make sure that they're in the central 2/3 or 3/4 of the image. So what is the effect of the beam width when we actually scan a tissue? This diagram shows that every point in that tissue is going to be smeared out horizontally by an amount equal to the beam width. I've drawn those smears as a series of discrete little lines, but in fact they will blur together. And the result is that the tissue looks thicker than it really is, and it looks fuzzy. So whenever you scan a tissue at an angle, it's going to be thickened in the image, and it's not going to be as clear as you would really like it to be. Yet again, our friend perpendicular incidence is a special case. When you're scanning at 90 degrees, the beam width effect isn't visible in the image because all that lateral smearing is superimposed on the image of the tissue. So we don't see any fuzziness. We don't see any thickening due to the lateral resolution. So there's a very good reason, when you want clarity of imaging of a particular tissue, to make sure that if you can, you're scanning it at 90 degrees. I'm sure vascular people already know this from experience. Here's an example, an image of a cyst. The red arrow is pointing to an area of substantial fuzziness because of the beam width effect. If you look at the more superficial boundary of that cyst, it's very much clearer. And there are two reasons for that. One is that it's a bit closer to 90 degrees incidence, and so it is less degraded for that reason. And the other is simply that the beam is considerably narrower at that depth, much better focused, and so there is less degradation of the image by the beam width effects. Here's a cardiac image, again showing examples of the fuzziness caused by the beam width effect. So the lower three arrows are pointing to a whole lot of areas where it looks quite substantially fuzzy. The upper area is highlighting the fact that close up to the probe and the area of interest, I think that's probably that piece of pathology, whatever it may be, is clearly defined. And that's because it's close to the probe and the focus marker, which is the green dot on the right of the image, has been set appropriately. So you can see a big difference between the clarity of the tissues in that region where the beam is well focused and the much fuzzier image deeper in. So beam width clearly has quite a profound effect on the image. Now let me talk about how the machine controls the width of the beam and focuses the beam. The most important ingredient in all of this is that the machine uses an array transducer. And that means the transducer, which is the active element in the probe that transmits and receives ultrasound, is sliced into a large number of identical thin slices, each of which can transmit and receive ultrasound. Each of those array elements is separately connected to the electronics of the machine so that it can pick and choose which elements it uses and exactly when it transmits and receives with each of them. The machine then has a series of electronic delays, and I'll show you a diagram in a moment, and these allow it to vary the exact time at which each element transmits, and also to change the timing of the received echoes to manipulate that. So the machine is using electronic delays to modify the exact timing of both the So the machine is using electronic delays to modify the timing of both transmitting and receiving. And this allows it to electronically focus and steer the beam in whatever direction it wishes. Here's the diagram I mentioned. In this case, we're looking at the transmit function. So the transmit pulse passes through a series of different delays before it's delivered to each of the elements. I've only shown a small number here for simplicity in the diagram, but there would be one delay for every single element that is transmitting. The timing has been arranged so that the beam will form in the tissues in the direction that I've shown with a large arrow, and there will be a time variation that causes it to focus at the appropriate depth the user wants to focus. So the user dials up a particular focal depth, and the machine then calculates all these delay values and applies them so that the beam will be in the required direction with a correct focus. When the machine is receiving, it delays the received echoes by varying amounts to achieve the same type of thing. Now, the interpretation of what the beam means is a bit different, depending on whether we're talking about the transmit beam or the receive beam. I've mentioned already the transmit beam tells you where the transmitted energy actually travels. So that's the pathway along which the transmitted energy goes, whereas the receiving beam defines those tissues which are capable of sending echoes back to the probe that the probe will detect. So any tissues outside of the receiving beam that happened for some reason to produce echoes, those echoes would not be detected. Only echoes coming from within the receiving beam will be detected by the machine. So each of them try to define as well as possible, as well as the machine can do this focusing, just exactly where the transmitted pulse goes and where the received echoes come from. There are several different ways of producing an image. I've been talking about standard grayscale imaging, which is called B mode imaging. B is for brightness, and it means that the brightness on the screen represents the strength of each echo. This diagram is, of course, an M mode, time motion mode image. And you can see the cardiac image at the top. The user has pointed a line pretty much vertically down the middle, but directed it so that it just passes through the tips of the mitral valve leaflets. That beam then remains stationary, and a series of pulses and echoes occur, so the machine is transmitting and receiving with the beam in the one fixed position. And so we see the echoes along that particular line and how they change with time. And so we see traced out in the image the motion of the mitral valves, the ventricular walls, etc. We can look at distances, separations, velocity, acceleration, timing relative to the ECG, which is the colored line that's superimposed. So lots of useful information in this image. The A mode image is ridiculously simple. This is a diagram of it. The idea is that, again, the beam is stationary, but this time the display simply is going to plot echo amplitude as a function of depth. In situations where there are a few isolated sources of echo, like the eye, where you've got a few structures separated by fluid, then you can get very accurate measurements between the tissues. And so that's the reason that A mode is used at all, is that while it's not really an image in any sense, it provides highly accurate measurements. So it's used in ophthalmology, and as far as I know, that is the only use of it. So we do have these three different modes. By far the most common, of course, is the B mode or grayscale image. Ultrasound probes, these are the three standard types of external probes. In the top left, we have a linear probe, which is classically used for peripheral vascular work because it fits nicely onto a flat surface and provides a broad image field close up to the probe. The curved probe is the ideal probe for abdominal use. You can push it into the soft abdomen and get contact over the entire curved face. It produces an image which expands with depth to give a large field of view. And so that's the favored probe for abdominal and obstetric imaging, for example. The cardiac probe down below is a phased array probe or sector probe. It's more compact because it has to use small windows into the anatomy, such as gaps between the ribs and the other windows that are used in echocardiography. So it's intentionally compact, and it produces, as you know, a quite different shaped image because of its scanning method. Now, I'm sure you're horrified by block diagrams, and even though I've tried to simplify this, it still is not a pretty sight. But let me talk you through it, and let's hope I can take some of the pain out of it. At the top, we have the transmitter, which is the electronics in the machine creating the transmit pulse. So it makes sure the transmit pulse has the right amplitude, the right frequency, the right duration, etc. It then sends the transmit pulses to the transmit beamformer, which contains all those delays I was talking about earlier. That then sends the transmit signals to the individual elements within the probe to create the focused beam and to steer it if necessary. As the ultrasound is traveling through the tissues, echoes are coming back, the machine is detecting those. The echoes go to the receive beamformer, which looks very similar to the transmit beamformer. Again, there's a whole series of delays which act to focus the beam and to direct it in the right direction. Once the received beamformer has operated, it combines the echoes together to form a single echo signal, which must then be amplified because it is so weak. So the amplifier simply makes the echo signal stronger. You have control over this amplifier. You have a gain control, a B gain, an overall gain control, whatever the machine may call it. And that allows you to modify the amount of gain applied to the echo signal. If you increase the gain, the entire image will get brighter. If you decrease it, it will get darker. And then we have the more specialized function known as TGC. That stands for time gain compensation, and its role is to correct for the effects of attenuation. I mentioned earlier that the signals, the echo signals, get weaker and weaker and weaker as they come from greater depths. The TGC ramps up the amount of amplification with time to compensate for that. And its aim is to keep the echo amplitude constant with time so that the effects of attenuation have been completely removed. So the aim is to make any particular structure look the same no matter what depth it's at, to remove that attenuation effect. We then have a function called compression that I'll talk about on the next slide, and that then delivers the echoes to something called the scan converter. The role of the scan converter is to take the echoes as they're coming in from the probe and after all this processing, and to determine where each echo must go in the image. That then allows it to place each echo in the appropriate part of the image memory. So as the echoes are coming in, the scan converter is busily putting the echoes into the correct places in the image memory, and so it's building up a complete two-dimensional image in memory. Once that image is complete, it is displayed. It's the latest image, it's the newest image, and it's displayed, and it displaces the previous image. And that's how real-time imaging works. There's a whole series of images, one after another after another. So as soon as one is ready to be displayed, the machine starts acquiring the next image. Of course, the image can also be transferred off to digital storage of varying types. I've shown some steps called pre-processing and post-processing that modify the information immediately before it's stored in the image memory and between the image memory and the display, but we don't really have time to talk about the details of that. Any questions about this before I move on? So compression is short for a big mouthful, dynamic range compression. The term dynamic range refers to the fact that there is a huge range of echo strengths. Tissue interfaces scanned at perpendicular incidence can produce strong echoes, particularly if there is a big difference in the first and second tissue. And so, whereas scattered echoes can be very, very weak. So dynamic range simply refers to the range of echo strengths from the strongest to the weakest. And the weakest is generally the lowest, weakest echo that the machine is capable of detecting. And so we have a ratio that I've shown here, the intensity of the strongest echo divided by the intensity of the weakest echo. And that's what we call the dynamic range. Commonly, we talk about this in decibels rather than just as a pure number. And that means we take the logarithm of the ratio and then we multiply it by 10. It's still the same dynamic range. It's simply using different units to talk about it. And decibels have some advantages, significant advantages. The typical dynamic range from normal tissue imaging is around 60 decibels. 60 decibels means that the strongest echo is 1,000,000 times stronger than the weakest echo. So there's an enormous range of echo strengths coming from the tissue. The machine has to display all of these echoes as varying brightnesses on the screen. This is where we run into a problem. The display can only handle round about a range of 30 decibels, in other words, a 1,000 to 1 variation of brightnesses. And our eyes can only really see that as well. So there's a mismatch between the echo strengths and how much they vary and what the display can handle. The machine therefore needs to compress the dynamic range of the echoes to match up with the display. And it does this basically by compressing strong echoes a lot so that they all look pretty similar. The logic for this is that normally the amplitude, exact variations in the strength of strong echoes is not very useful clinically, whereas variations in echo strength of soft tissue echoes, low-level echoes, are important. And so the idea is by compressing the strong echoes, you maximize the ability of the image to show variations in soft tissue echogenicity. So this graph shows a typical compression curve. On the horizontal axis, we've got the echo intensities spreading over a total range of 60 decibels. On the left-hand end is the weakest echo the machine can detect. On the right-hand end is the strongest echo it's going to receive. On the vertical axis, we've got the brightness on the display. Again, a logarithmic scale in decibels. If I look at a mid-range echo, so an echo that has a strength at the 30 decibel mark, then I would draw a line as I've shown here, the dotted line, and then go across to the vertical axis, and that tells me what brightness will be displayed on the screen for that particular echo strength. And it's showing me that that the brightness on the screen is at the 25 dB mark, which is quite close to white. Not quite white, it's a very pale grey, but it's getting close to white. If you now look to the right of that 30 dB mark on the horizontal axis, that's all the strong echoes. So that's going to be echoes predominantly coming from reflections from tissue interfaces. And you can see that on the display, those are spread over just the range from 25 to 30 dB. In other words, light grey to white. If we look at the bottom half of the echo intensities from 0 to 30 dB, you can see that those lower level echoes are spread over most of the display range on the display from 0 to 25 dB. So as the echo intensity varies, for the low level echoes, we'll see significant changes in brightness on the screen, and we'll be able to differentiate regions of different echo strength. So that's the logic of the compression function. Ultrasound has important limitations, and it's your role to know those and to work within those limitations. So let me just review them very, very briefly. Attenuation, I mentioned it right in the beginning today because it is one of the most important. And in particular, it limits the depth of penetration. That means if we do need to go deeper, we have to use lower frequencies. We have no choice, unless we want to use invasive probes, of course. I talked about the fact that the machine has to wait for the echoes to come back for each beam position before it moves the beam. And that's going to limit how many times the machine can transmit per second. That's called the pulse repetition frequency. So limiting the pulse repetition frequency in turn limits the number of images the machine can make each second, which we call the frame rate. So the number of images per second is going to vary depending on depth. If I'm looking very superficially, the frame rate will be high. If I'm looking really deep, the frame rate is going to be much lower. At times, and I imagine this happens particularly in echocardiography, the frame rate isn't good enough and you need to know what to do about this. In this case, you need to reduce the image so it takes less beams to make each image. You do this by narrowing down the image. So for example, if it is a sector scanner, you narrow down the sector and then each image can be made more quickly. The other thing you can do is to turn off some of the optional extra modes that the manufacturers have introduced over time, because almost all of these slow down imaging. So you would turn off multiple focus markers, compound imaging, harmonics, color Doppler, etc. And if you just went back to straight standard grayscale imaging, you'd find you've maximized the frame rate. The other limitation, which we haven't talked about in detail because that's going to be covered next term, is image artifacts. An artifact is defined as some appearance in the image which doesn't accurately reflect the tissues that are being imaged. So it's extra echoes that shouldn't be there, it's distortions of things that are there, it's inability to display things or duplication of things in more than one different place, etc. So there's a whole series of image artifacts which take a significant time to talk about themselves. But the important thing at this point is to say they degrade the image. They make it harder to see things in the image. They can at times even potentially mislead you. And so you need to understand image artifacts very well and know how to recognize them and to minimize them. And that brings me to a very important concept, which is the idea that part of your role is to optimize the image. We've talked about the limitations. And so the question is, how do we minimize those limitations? How do we get the best image we can? And hello, am I back?
Rob, so we missed you for about 90 seconds or so.
Yeah, I'm going to walk myself right up close to the modem.
Okay.
So if there is any background noise, we'll just have to live with that.
Yep.
Fortunately, I can take my jungle with me.
It's impressive. Yeah, it's about, I don't know, if you were to go back a couple of slides. At the most.
Thanks, Paul.
Thanks, Rob.
So perhaps about here?
No, a little bit further on, maybe. Keep going.
Limitations?
I think so.
Okay. So ultrasound's limitations are very important, and you need to have a good, clear idea of what they are, because they degrade the image in many cases, but they also need to be worked around and their effect has to be minimized. So the first one, which I talked about at the very beginning of this afternoon, is attenuation, which limits the depth of penetration. And the higher the frequency is, the more limited the depth of penetration will be. So in the end, attenuation and depth between them dictate what frequency you can use. When you're scanning superficially, you have to use really high frequencies. You can use really high frequencies and get lovely resolution. But when you're scanning deep, you can't do that. You have to use much lower frequencies and live with poorer resolution. The depth also limits the number of images that can be made each second. And this is because of the rule I mentioned earlier, that the machine has to wait after it's transmitted for all the echoes to come back and for there to be no more echoes that are detectable before it moves the beam to the next position and repeats the transmit process. So the deeper in your scanning, the longer the machine must wait in each position, in each beam position, before it can move to the next beam. So the deeper you're scanning, the longer it takes to acquire each image, and therefore the less images per second there will be. So there's a direct link between depth and the frame rate. There are times, particularly in echocardiography, where you may find the frame rate isn't adequate. And in that case, you need to know what you can do to improve the frame rate, to increase it. There are two things. The first is you can reduce the number of beams that it takes to create the image. And you do this by narrowing the image. So if we're talking about a sector probe, we narrow the sector and make the image narrower, so there's less tissue being imaged, but the frame rate will go up accordingly. If you halve the width, the frame rate will double. Curve probes also have the same capability. I'm not so certain about linear probes. Some may, some certainly don't. So that's one approach. And then there's a second thing, and that is that many of the additional things that the manufacturers have introduced over the years that enhance ultrasound also slow it down. And so things like multiple focal depths, compound imaging, harmonic imaging, and color Doppler, all of those slow down the imaging rate. Harmonics, for example, halves the frame rate approximately. Compound scanning slows the effective frame rate very dramatically. So if you're having trouble with frame rate, you turn off those modes as much as you possibly can. And you'll see that the frame rate will gradually increase as you get rid of extraneous functions. The other thing that degrades image quality, which we'll be talking about in detail next term, is image artifacts. These are echoes that appear in the image which aren't accurate representations of the anatomy. They may be related to the anatomy but appearing in the wrong position. They may be due to distortion of the anatomy in the image, or they may be entirely unrelated to the anatomy caused by some of the artifacts that we'll talk about next term. So image artifacts are important because they put echoes into the image that are cluttering up the image and making it harder to see the real thing. And so one of the things that you need to know is to recognize image artifacts, to know what they are, what their cause is, whether they're telling you something useful, but also how to minimize them because they are degrading image quality. And then this brings me on to an extremely important concept, which is that part of your job is to optimize the ultrasound imaging. Because of the many limitations I've just reviewed, you need to optimize the image. In other words, to minimize the impact of those limitations. You need, for example, to make sure you're using the right frequency, not a frequency way lower than you need to, because you want to get the best resolution you can. So basically, there are two different types of things you can do to optimize the image. And the first of those is to use really good scanning technique. And of course, that's what you are learning in your practical experience, is gradually picking up technique, tips, alternative approaches, etc., which help you to get better images. But the second half of it, which is more in my domain, is that you need to know how to properly use the machine's controls to operate the ultrasound image. And just remind yourself that you really do need to use those controls, because your job is to get good diagnostic images, not suboptimal images that may not provide all of the diagnostic information that is needed. So just see optimization of the image quality as part of your job. So I'm sorry for the technical glitches with inadequate networking. If you need an excuse, I've got one for you. I've just been put on the NBN and it's not as good as what I had before, like so many other people. So there's my excuse. Anyway, do I have any questions at all? All right, well, we'll move on to the third lecture, which covers quite a big subject, because in one lecture, we're covering all of Doppler ultrasound. So let me move on to that. Doppler, of course, is used to look at blood flow, and therefore it's essentially looking at functional aspects as well as imaging at times. It's based on the fact that ultrasound is scattered by blood. Now, I need to say this because in an ultrasound image, you can't see blood. Normally, blood looks completely echo-free in the grayscale image. There are occasions where it might become visible in special situations, but normally the scattering from blood is too weak for it to be visible in the grayscale image. But the machine, with the right conditions, can detect the scattered echoes from blood, and that's the basis of Doppler. So Doppler's looking at the echoes coming from moving blood. The reason that the word Doppler comes in here is because of a phenomenon, and that is that the echoes from blood that is moving, when we look at them really closely, will have a slightly different frequency than the frequency the machine transmitted. For example, the machine might be transmitting 5.0 megahertz ultrasound pulses, and the echoes coming back from blood may have a frequency of 5.001 megahertz. That means that the received echoes have a frequency that is just 1 kilohertz higher than the frequency that the machine was transmitting. That change of frequency is what we call the Doppler effect. And the difference between the received frequency, the frequency of the echoes, and the original transmitted frequency, that difference of frequency is called the Doppler shift. So the machine is able to detect the echoes from the moving blood and their frequency in order to detect whether or not there's a Doppler shift. If there is a Doppler shift, it's capable of actually measuring it, quantitating it, and displaying it. Now, the display may be as a color image overlaid on top of a grayscale image, and we call that color Doppler, or it may produce a spectral display, which shows a waveform. In other words, a varying signal which shows us how the blood velocity in a vessel or in the heart is changing with time. And that can be acquired with either pulsed Doppler or continuous wave Doppler. So we actually have 3 different forms of Doppler instrumentation. But let me just talk about first a couple of examples and then about some further details of the principles. On the left here, we've got a cardiac image with color Doppler displayed. And so we can see the colors representing the fast-moving jet through this insufficient aortic valve. The user has then positioned a beam, which you probably can't see, but there's a small dotted line passing down the direction that they've selected to sample Doppler signals using a continuous wave Doppler. And that's what's produced the waveform in the right-hand half of this image. So this tracing shows us the velocity through the aortic valve, dramatically increased velocities due to the insufficiency. And we can see the way this varies with time. You can look at timing versus ECG, etc. So this is a very, very valuable tool, and it can provide estimates of pressure drops and regurgitation fractions and all sorts of things. Here we have a second example, which is a vascular example. So we've got a blood vessel. This is again a color Doppler image, and you may be able to see that there's a box that defines the region where color has been acquired, just as in the cardiac image, in fact. And we call that the color box. The color box in the lower image has been steered, so it has an angle to it. And the beam that is shown passing down roughly the center of the image is also steered in that same direction. That's been set by the user so that there is an appropriate angle between the ultrasound beam and the flow direction. Because we'll see shortly, this particular angle between the beam and the flow is very important. There is then a small sample volume that the user has positioned in the center of that vessel, and that's acquiring Doppler signals, which are shown in the waveform tracing, the spectral waveform below. You can see a radically different pattern of flow in that artery than in the heart, of course. And you can see whether that's a normal pattern for that particular vessel. Look at peak velocity values and other parameters that you can derive from that waveform. So how do you go about doing an acquisition with continuous wave and pulse Doppler? You would select Doppler mode, place the sample of volume in the area that you're particularly interested in the case of pulse Doppler. With continuous wave, you may or may not be able to guide it as to where it gets the data. I'll show you shortly that continuous wave has a very, very large sample volume, and so you may or may not really be able to say where its main area of focus is. In the case of vascular work, you will then align an angle marker parallel to what you believe is the direction of blood flow. This is very, very important because otherwise the machine isn't able to calculate velocity values from Doppler shift values. So you align an angle marker that informs the machine what direction the blood is flowing in. In echocardiography, a lot of the time you're aiming to have the beam parallel to flow, and in that case the angle is very, very small, and I'll be showing you shortly it's really not so important, and you often won't be doing any angle markers or angle correction. So the angle correction is predominantly seen in vascular applications. You can then turn the Doppler on and check the major settings, so make sure the gain is appropriate, the Doppler display scale and baseline position are correct, and so on. You can then freeze the waveform, make measurements from it, etc. With color Doppler, you select the color Doppler mode and a color box will then appear in the image. You can then position that, change its size. If you're using a linear probe, you can also angle it to get an appropriate beam to vessel angle. But that's going to be in vascular applications. Then you can activate the Doppler, once again, check all of the scales and settings are appropriate and so on, and acquire your information. And here would be another typical color Doppler image in the heart. So the equation that relates blood velocity to the Doppler shift is shown here. The Doppler shift is 2 times the ultrasound frequency multiplied by the blood velocity multiplied by the cosine of the Doppler angle. The Doppler angle is the angle that I've been talking about between the beam and the flow direction. So you can see that the Doppler shift is influenced by both how fast the blood is going and the direction it is traveling relative to the beam. The machine is going to measure the Doppler shift and it wants to calculate the velocity from that. So it must know what the angle is. If you don't help it by putting an angle marker in, it assumes that blood flow is parallel to the beam, that the angle is 0, and we'll see shortly that the cosine of 0 is 1. So it can then ignore the cos theta effect. So normally in vascular operations, you'll be angle correcting, telling the machine the flow direction. It will then figure out the Doppler angle and it will incorporate it into the calculation. In echocardiography, commonly you assume that you're getting the beam pretty much parallel to flow. The machine therefore accepts that assumption and leaves out the cos theta term. Here's a graph showing Doppler shift as a function of the Doppler angle and the ultrasound frequency. So Doppler shift is on the vertical axis in kilohertz. And one of the very nice things that happens in ultrasound is that the Doppler shifts just happen to fall within the range that we can hear. We can hear frequencies of 10 kilohertz and even up to 20 kilohertz with good hearing. So you can listen to the Doppler signal and monitor it by ear, and that's standard practice. That's pure good luck that happened. It's nothing that anybody set out to design. Now, this particular graph is for one particular velocity value of 100 centimeters per second, which would be a fairly typical peak value in a large artery. So we can see that the Doppler shift just increases directly in proportion as we change the ultrasound frequency, as the equation predicts. But the variation with angle is really more interesting. What we see is that when the angle is 0 and close to 0, in other words, when the beam is parallel to flow or nearly parallel to flow, we get the maximum possible Doppler shift. However, as the angle increases, the Doppler shift decreases, slowly at first, but then more rapidly, until eventually at 90 degrees, there is no Doppler shift at all, no matter what the velocity, no matter what the ultrasound frequency. So at 90 degrees, there will never be a Doppler shift. We'll learn later on there's an artifact at 90 degrees, but not a real Doppler shift. Now, as I said, the machine uses the angle marker when we're doing angle correction. It uses U to tell it what the flow direction is relative to the beam. Even in echocardiography, it assumes you have a line to the beam if you haven't told it otherwise by setting an angle marker. So it is on your shoulders to help the machine know what the Doppler angle is. Unfortunately, you're never going to be 100% accurate in doing that. It's impossible to set it perfectly. You're only doing it by eye. It's relatively small. But also, equally important, you don't know the exact direction of flow. In a blood vessel, the normal assumption is blood's going parallel to the vessel walls, but it isn't always. In the heart, of course, particularly in the presence of pathology, flow directions can be quite surprising, with quite erratic jets of blood sometimes with diseased valves. And the same is actually true in vessels with vascular disease. So at best, you're estimating you and the machine between you are estimating the Doppler angle, and there's likely to be a little bit of error. So the question then is, if we suppose that there may be as much as 5 degrees error in your determination of the Doppler angle, what's the effect of that on the velocity measurement? And this shows the answer to that. When you have a very small angle, and ideally in echocardiography, you're aiming for an angle of 0 degrees, then this really doesn't matter. You're not bothered by it. You really don't care about it. But vascular people are often operating at around an angle of 60 degrees. And that's forced upon them by the anatomy and the geometry of the situation. They have little choice. So for a lot of peripheral vascular and cerebrovascular work, you have an angle of around 60 degrees. What we can see then is that a 5-degree error in angle would cause a 15% error in the velocity measurement. And that's pretty much the upper limit of what is acceptable in a measurement like this. So there is a general consensus, therefore, that you should not make measurements from Doppler signals that have been obtained at angles greater than 60 degrees. In other words, 60 degrees is about the biggest angle you should be using. A few words about blood as a scatterer. As I've mentioned already, blood is obviously a very weak scatterer since we can't normally see it in the grayscale image. In order to make the blood echoes detectable, when the machine is operating in Doppler mode, it transmits more energy. And so the transmitted pulse has to be more energetic when the machine is doing Doppler than it is for imaging. Usually this is actually achieved by making the transmit pulse duration longer, because it turns out this is better from a safety point of view than increasing the amplitude of the transmit pulse. So with Doppler, it's typical that the transmit pulse is a bit longer in time, and therefore there is extra energy transmitted, and so the patient exposure to ultrasound energy is increased. It's higher than it would be in grayscale imaging. Then there's a second consideration. For continuous wave and pulse Doppler, the beam's stationary. It's not scanning around through the tissue, spreading the ultrasound energy around, it's still. And so only that small amount of tissue that is within the beam, that's getting all of the transmitted energy. So it's getting a high level of exposure. And so the result of these two considerations is that Doppler normally, and in particular pulse Doppler, normally causes the highest levels of exposure, of patient exposure. And so when you're doing pulse Doppler, is when you most need to keep an eye on the safety parameters that are displayed on the screen. Are there any questions so far before I race on? All right, what we're looking at here is how the machine internally calculates the spectral display. And so we've got a particular arterial waveform, and then we see that we have a horizontal time axis spanning several seconds. We have a vertical axis that I have marked in kilohertz, because that's what the Doppler shift is. It's a frequency change of the echo frequency. And most importantly, I've marked the upper and lower bounds of what the machine can detect and correctly display. And those bounds are called the Nyquist limit. That Nyquist limit is a particular frequency. It's, in this particular example, 4 kilohertz. The way you find out what the Nyquist limit is very, very simple. You look at the Doppler pulse repetition frequency and you divide that by 2. So the Nyquist limit is 1/2 of the Doppler pulse repetition frequency. Now, here we can see a waveform above the zero line, above the baseline, and you'll notice on the right-hand side, with the markings on the axis, it's saying that those are positive Doppler shifts. That means the blood is coming towards the probe. If the blood was moving away from the probe, there would be a negative Doppler shift, and the display would be below the baseline rather than above the baseline. So the direction of flow relative to the probe is indicated by whether the flow is above or below the baseline. Now, I said that this is what the machine has got internally. Here's what it displays externally. It's the same display, but with one important difference. It's calculated velocity values from the Doppler shift values. The display is still the same, but now we can read off the velocity values. As I've mentioned several times, to do this, it must know the Doppler angle. Otherwise, these values are meaningless. Now, I mentioned the limits. If you imagine that we had a high Doppler shift that actually exceeded the limits, we would have a problem. And that's a particular artifact that's known as frequency aliasing that we'll cover in detail next term. But there's a very, very simple thing that can be done about this. And that is that the baseline of the Doppler display doesn't have to be in the center. You can shift it down, as has been done here, and then you can display a larger range of Doppler shifts above the line, and you've paid a price in that you can only show a much smaller range of Doppler shifts below the baseline. And so moving the baseline is in fact part of standard practice, not so much in echocardiography perhaps, but certainly in other areas, in order to maximize and make best use of the Doppler display. Let's talk for a moment about pulsed Doppler instrumentation. Actually, let me take a very, very short break to grab a glass of water. Okay, that's got me going again. So pulse Doppler is basically quite similar to imaging in many ways. The machine transmits a pulse and then it waits for the echoes to come back from the tissues. However, there's something very specific about pulse Doppler. The machine is only interested in the echoes that come from the place where you position the sample volume on the screen. So the machine calculates the depth of that sample volume and therefore knows how long it must wait for the echoes to be coming back from that specific depth. It will then look at the echoes briefly for maybe a microsecond coming from that particular depth. It ignores the echoes that have come earlier. It ignores the echoes that come later. It looks only at the echoes coming from the sample volume. So it's sampling the echoes from the depth of interest, which is where you place the sample volume, ignoring all others. And there's a term used for this, it's called range gating, because range means distance away from the probe. So this process goes on and on. The machine transmits, then range gates, and then transmits again, range gates again, and so on. And so that goes on continuously. And the machine has, at any one time, is going to look at the most recent 128 transmit pulses and the echoes that have come from those 128 pulses. It's then going to analyze those and detect the Doppler shift from that bunch of pulses and then process the Doppler shift. Now, one of the important things I haven't mentioned yet is that echoes from moving tissue can be a problem because tissue is a stronger reflector than blood, and tissue moves and therefore produces Doppler shifts as well. Luckily, though, tissue moves more slowly than blood. And so the machine has what's called a wall filter, which removes the Doppler signals, the low frequency Doppler shift signals coming from moving vessel walls or cardiac walls. So graphically, here we've got the setup of a pulse Doppler measurement. You've got a blood vessel. You've steered the beam in an appropriate direction so that you're going to end up with a Doppler angle of less than or equal to 60 degrees. And you've set your sample volume in the center of that vessel. As soon as you do that, the machine can calculate the depth, D, and so it knows the exact time the echoes will come back from that sample volume, and therefore exactly when to sample the echoes in order to detect the Doppler shift. And this is highly selective because the range gate, as I'm showing in the diagram below, is small. As I mentioned earlier, it may be a microsecond or less in size. In fact, the size of the sample volume can be increased and decreased. It can be as small as a millimeter typically, and it may be made as large as 10 millimeters if you really want it to be big for some reason. And so in the diagram at the bottom there, you can see the general idea. Transmit a pulse, wait the appropriate amount of time, sample the echoes briefly with the range gate. And then once it's okay to transmit again, do that, and then the process repeats over and over. Here's the processing where we've now got transmit pulse, range gate, transmit pulse, range gate over and over again. The information from the most recent 128 range gates is gathered together, combined to produce the Doppler signal. The wall filter then removes the low Doppler shift part of that Doppler signal that's likely to be coming from moving tissues. At that point, we've got an audible signal we can listen to, but it also then goes to the machine's spectral analysis, and that creates the waveform display that I've shown you examples of. So that's the fundamentals of pulsed Doppler. Color Doppler, perhaps surprisingly, is based on pulsed Doppler. So the same concept, but with a number of huge differences. So the first difference is instead of one range gate, there are lots and lots of range gates. So for a given beam, there's going to be range gates extending all the way through the color box because those range gates are going to require all the information necessary to make the color image. So each beam has many, many range gates. The next difference is that with the beam in any one position, the machine transmits and receives just 8 times. So it acquires only a very small amount of information, and then it moves the beam to a new position and starts over. So the machine only has information from 8 transmit pulses to determine the Doppler shift and to quantify it and display it. So the machine is working with information from 8 transmit pulses in color Doppler. In pulse Doppler, it's using information from 128 transmit pulses. So you can see that the information from pulse Doppler is going to be more accurate, more fine detailed, etc. And the information from color Doppler is going to be less accurate and probably have some limitations. But of course, that particular shortcut is necessary in order to produce real-time images of Doppler. When color Doppler was first revealed to the world by its developers, none of us could believe that it was possible. It just seemed beyond what was possible. And what that tells you is that it's doing something very difficult and having to make a lot of compromises in the process. So the beam is going to step from one side of the color box to the other, with just 8 transmit pulses being transmitted in each position, and that will acquire all of the information necessary to make one color image. So if I now say, well, what happens to those 8 samples, the 8 echo samples from each individual sample volume on each individual beam? So if I thought about one particular sample volume and I say, well, what do we get from that sample volume? There's a mathematical processing. The wall filter is applied. Excuse me. The machine calculates just 3 numbers. These are the mean or average Doppler shift for blood that is in that particular sample volume. So the mean Doppler shift, and that's the thing that's actually displayed in color. Second parameter is called variance, and like in statistics, it's a measure of variability. In this case, it tells us what the range of Doppler shifts is within that sample volume. So whether there's a wide range of Doppler shifts, which would indicate disturbed blood flow, or a relatively narrow range of Doppler shifts, which would be normal. And then the third parameter is the strength of the Doppler signal, the Doppler power. So the mean Doppler shift is converted to a color. And the machine displays that on the image, but only in places where the machine determines that it's looking at flowing blood rather than looking at tissue. So the machine has a function that discriminates between tissue and blood, and it only shows color where it should. Now, particularly in echocardiography, it's quite common to use a second color, often green, to highlight areas that have abnormally increased variance. Because as I mentioned a minute ago, a wide variance means a wide range of Doppler shifts in a small area, and that suggests that you may have disturbed blood flow rather than normal blood flow. So it's a likely indicator of disease. The color image always has a color bar, which I think I pointed out to you in the one example, and that tells you how Doppler shift is being converted to color. It's possible to change the vertical scale of the color, just as it is in pulse Doppler, possible to change the vertical scale of the Doppler. And in color, it's also possible to shift the baseline up and down, just like in pulse Doppler. So this might be what's happening internally for the color Doppler, that we've got a beam being transmitted. We've then got a whole series of range gates. And for each one of those range gates, the machine is calculating the 3 parameters I just described to you. So this will produce a beam in a particular position. You see there's a whole lot of sample volumes being created by those range gates. extending from the top of the color box to the bottom of the color box. And so that's acquiring the information that's going to be converted to color and displayed down that particular beam line. The color bar I've already talked about on the left here, at the moment has the baseline in the center. The fact that red is above the baseline tells us that anything that is colored red must be blood that is flowing towards the probe. Anything that is blue is blood flowing away from the probe. The numbers at the upper and lower limits of the color bar, 35 centimeters per second, represent the machine's calculation of the velocity that would just reach the Nyquist limit. So the Doppler shift at the top of the color bars would be equal to the Nyquist limit on half of the pulse repetition frequency. Now, it's important to recognize that that value is calculated without any angle correction. So in echocardiography, it's likely to be meaningful. In other applications of Doppler, where you're probably not operating with an angle, with a beam parallel to flow, these values are misleading because they're calculated assuming the beam is parallel to flow. Obviously, in this example, we probably have an angle of around 60 degrees. Clearly, these 35 centimeter values, centimeter per second values, are completely unrelated to the true velocities in those vessels. Continuous wave Doppler is different and in fact very much simpler than color and pulse Doppler. Half the probe is transmitting ultrasound continuously, and the other half of the probe is receiving ultrasound continuously. So there's no pulsing at all, no selectivity about range or depth or anything else. We're just transmitting ultrasound and receiving the echoes all the time continuously. Now, the fact that it's continuous gives continuous wave Doppler one huge advantage. And that is that it can measure velocities that are very, very high. Pulsed and color Doppler have real trouble with high velocities, and this is why CW Doppler is routinely part of an echocardiography machine. Now, I said that there's no sort of selection of depth, but there is in a crude way. The region where the transmitting beam and the receiving beam overlap one another essentially defines the sample volume of the continuous wave Doppler. And I'll show you a diagram in a second. The important thing to notice is that the sample volume is much, much bigger than the sample volume that you get with pulse Doppler. So continuous wave Doppler is great because it can measure high velocities, but it's not good because you can't really tell exactly where the Doppler shift is coming from. So here's the diagram. We've got one half of the probe transmitting, and I'm showing the transmitted beam with the green lines, and then the other half of the probe is receiving, and so that's shown with the purple lines. Now, there are handheld Doppler probes, and they'd probably have two separate transducers angled relative to one another, as in this diagram. But if you're doing continuous wave Doppler in echocardiography, it's likely the machine is using one half of the probe to transmit and one half of the probe to receive, and it's steering the beams like this electronically. So the important point here is that the gray zone, which is where those two beams are overlapping, is the sample volume of the continuous wave Doppler, because those tissues are receiving transmitted ultrasound, they're inside the transmit beam, and echoes from those tissues will be received because they're inside the receiving beam. So that overlap region is the sample volume of the continuous wave Doppler. And you can see it can be very, very large. So why are there three kinds of Doppler? Pulsed, color, continuous wave. And the answer is that they each have a separate role. Pulse Doppler gives detailed quantitative velocity information from one selected point. And you can position that point anywhere at all within the grayscale image and get that information. But pulse Doppler has the really important limitation that you cannot measure very high velocities because the Doppler shifts will exceed the Nyquist limit and you won't be able to display them correctly. So we come back to that, remember, next term. Continuous wave Doppler, on the other hand, can measure those high velocities, and so that's why it's used in echocardiography, but it has this large sample volume. Luckily, in the situations where we have extreme high velocities, we normally know that that's only in one part of the heart, and it doesn't matter if we're picking up low velocity information from other bits of the heart when we're using continuous wave Doppler, because we can still be confident that it's the high velocity bits that we can see clearly which are the things of interest. Color Doppler is different from these two. It's not quantitative. For example, you can't angle correct color images. So it is more of an image and a map showing you where blood flow is, highlighting areas where there's abnormal velocities. But you must be very careful not to interpret too much from variations in color, because those variations may be due to changes in velocity or changes in the Doppler angle. So that brings me to the end of this really whirlwind tour of those 3 lectures. The next lecture, which will be coming up in a few weeks, is going to talk about hemodynamic concepts. In other words, a few of the fundamental concepts that help to describe how blood flows and how it changes in disease. And that, of course, is really important to understand in order to know how Doppler ultrasound is used diagnostically. Next semester, or next term, as I've mentioned before, we'll be talking about Doppler artifacts in significant detail, as well as imaging artifacts. So, finally, can I ask if there are any questions before we draw this to a close? I know we've reached time here. Any burning questions? Okay, well, I'm going to have to bring the seminar, the tutorial to a stop because there are other things that need to happen.
Rob, if I can just
yes, Paul.
Interrupt just a little bit. Thank you for taking the time to explain things slowly and providing a really comprehensive tutorial on the first 3 lectures. Everybody, I'm sure you come to appreciate that Rob's able to explain difficult concepts clearly and simply. You'll have the benefit of being able to access this recording again. It will be available to you anytime. So I strongly encourage you to do so again and look at the notes that Rob's given, the lectures as well. If you do have any questions that pop up, please send them to me. I may not be able to answer them, but I'll certainly send them on to Rob. For vascular people, I encourage you to send yours to Donna, and she'll do the same. And please don't feel as though you're unsupported. I'm sure Rob will be able to and be very happy to answer any of your questions.
Absolutely.
So thanks, Rob. Thank you, everyone. I'll ask Rob in a moment just to bring this meeting to a close. The cardiac people will switch over to another line, another views line, and I'll wait for you there and see you shortly. Vascular people, thank you. Rob, thank you very much.
Okay, bye.